This mini lecture and example will illustrate the methodology required to test a claim that is being made about a population proportion, and using formal hypothesis testing procedures, you can come to a conclusion. So as before, when we were talking about proportions, remember that proportions, that's the percentage or fraction of a population that has a specific characteristic. And remember that the symbol for population proportion was P. And Q, of course, is the complement of that. So it's like a probability. So if P is the proportion that we want to test a claim about, Q is the 1 minus P. When we use the binomial distribution, we end up with, the mean was something like n times P, and the standard deviation was root NPQ. In order to test a claim about the population proportion, we need to then do a sample. And from that sample proportion, we will see whether the sample lies far away from the claim, significantly far away, statistically significantly far away, which would allow rejection of a null hypothesis. And so this symbol, P hat, with a little caret on top, that is your sample proportion. And the way that you calculate that is just exactly the same way we were doing this with confidence interval testing. You count the number of times that you find the characteristic that you're looking for, and you divide it by the total number of trials for the experiment, or the sample size of the experiment. And so in order to do this testing, we assume that we are dealing with large enough sample sizes so that we are going to have a normally distributed proportions, normally distributed samples of proportions that are about the population proportion. And so that basically we need these conditions to be satisfied, that NP and NQ both have to be bigger than or equal to 5. And under those conditions, to get a normal distribution, under those conditions then we can use the test statistic of a z-score. And we use the exact same calculation of z-score that we did previously. We take the sample proportion minus the claimed proportion, and we need to divide by something from the central limit theorem. Take the standard deviation of the population and divide by root n. You get something like PQ over n inside that square root. So we need to construct our hypothesis test as normal. Sketch your, you figure out what the claims are, you sketch your distribution, but you use the test statistic that is z-score, and then you look it up. Once you know your area, you look it up on the z-score table, and you find the appropriate z-score for the area that you have, and then use that to determine your critical z-score and see if your sample z-score actually lies in the rejectable region or not. So here's a typical example that you might see on a test where you have to test a claim that is being made about a population proportion. In this example, a company that is manufacturing aircraft pitot tubes, and pitot tubes are little Bernoulli tubes which mount on the side of the aircraft, and they use fluid flow velocity measurements. And what they do is, using Bernoulli's equation, you can come out with the airspeed of the aircraft. And they find that the manufacturing process that they are using gives a 7.5% defect rate. And of course, that's relatively high, so they want to test other alternative processes. A new alternative process from a competitor has led them to claim their new pitot tubes have a defect rate that is less than this 7.5%. So in order to test the claim, a sample of 755 pitot tubes of the competitor were tested. 38 of them were defective. And so if we have a 0.01 level of significance, we need to test this competitor's claim. So if we look at the formal hypothesis testing procedure, the first step is to write what the claim is. The claim that is being made is that the defect rate, and so that's a proportion, it's a claim made about a proportion, is less than 7.5%. So it has to be less than 0.075 as a decimal fraction. And the next step is to determine whether that is the alternative or the null hypothesis. Remember that the null hypothesis must have a statement of equality. And so this claim does not contain an equal sign, and so it must become the alternative hypothesis. Which means that the null hypothesis, the opposite of this, has to be greater than or equal to. So we only ever sketch and test the null hypothesis. The null hypothesis says that the proportion is bigger than or equal to 0.075. So if I draw a sketch of this claim, the value of population proportion of 7.5% is in the middle of the distribution. And according to the null hypothesis, anything bigger than or equal to this proportion is fine. So only if we find our sample gives us a value that is significantly less than that claimed proportion would we find evidence to reject the null hypothesis. And so right here, we were told alpha is 0.01. Because this is a left tail test, a single tail test, the entirety of the area is contained in that region. We need to find the critical z-score that corresponds to this area of 0.01. The area of 0.01, if you look at the z-score table, an area of 0.01 is close to 0.0102 and 0.0099. Somewhere between these two values, it's slightly closer to this one. So I'm going to choose a value of negative 2.33 to correspond to that z-score. So the critical z-score that separates the rejectable region from the acceptable region is negative 2.33. So in order to test this, all we have to do is find whether our sample lies significantly below this population proportion of 0.075. If it is in the critical region, we would reject the null hypothesis and therefore support the alternative. So we need to calculate first our sample proportion. It is the number of defects that we would find over the sample size. So that's 38 over 755. And so that is a sample proportion of 0.050331113. Clearly, that number, 5% defects, is definitely less than 7.5% defects. But is it significantly less? And so, in order to calculate the whether it is significantly less or not, we have to calculate the test statistic, which in this case is z-score. We take sample proportion minus population proportion that is claimed and divide by PQ over N. So notice we are going to need the claimed proportion, 0.075, 7.5%. Q, therefore, which is the complement of this, must be 1 minus 7.5%. That's 92.5%. So both P and Q are given, and so we can plug this in. The sample proportion of 0.050331113 minus the claimed proportion of 7.5%, but all divided by the square root of 0.075 times 0.925, all divided by the sample size, 755. And so N was given there, 755, and the number that was found was 38. So to do that z-score calculation, 0.05033111258 minus 0.075, all divided by the square root of 0.075 times 0.925 divided by 755. All of those are in the square root. We end up with the z-score for the sample is negative 2.57. 2.57 for the sample is less than the critical z-score of negative 2.33. So that places the sample here. It is lower than the sample claimed proportion of 7.5%, and it is also significantly lower to a 1% significance level because it is in that rejectable critical region. So we have the result that this score does lie in the critical region. Because that score lies in the critical region, we therefore must reject the null hypothesis. And so the way that you phrase your conclusion, it is always in relation to the original claim. The original claim was the proportion was less than 0.075. That was the alternative hypothesis. So we must phrase our conclusion based on the alternative hypothesis. If we reject the null hypothesis, we have therefore evidence to support the alternative. So your conclusion would be written, there is sufficient evidence to support this competitor's claim that P is less than 0.075 to a 1% significance level.